are an idea in which we combine two functions into one. So a piecewise function is literally piecing together two functions into one. Piecewise functions are something you will be using in algebra 2, algebra 3, which is pre-calc, algebra. Beyond that, if you go into any mathematics field, if you take AP Calc, we use piecewise functions all the time. So what we're going to learn today isn't just something, oh, hey, we learned it, and then it kind of disappears. No, piecewises are going to remain with us for a while. The idea and origination of a piecewise function came from Newton and Leibniz, and their idea evolved from calculus. So 2-6 is all about special functions. Our objective is to write and graph piecewise. We're going to look at piecewise functions for the remainder of this week. We're going to also go back to linear regression, and on Friday take a quiz on the 2. Next week when you come back, we're going to actually look at the step and absolute value functions. So some new vocabulary. A piecewise defined function is a function that is written. That's weird. A function that is written using two or more expressions. A piecewise defined function is a function that is written using two or more expressions. And then the expressions are defined by applying different rules for different domains. A transition point, also known as the breaking point. A transition point, also known as a breaking point, is the point on the function where the piecewise changes its domain elements. It is a point on the function where the graph changes its domain elements. Okay, sorry. Let me get your lunch count, though. I guess that's more important than ever. All right. So again, a piecewise defined function is split into its top, middle, bottom. If you have more than two equations, then it gets split into a top, middle, bottom, bottom. So every time you have a new equation, it can alter or change. If it is a less than but not equal to, then it is an open circle, just like when we graphed linear inequalities before. So on the graph where we graph 1/2 x plus 3, that will be an open circle. For the bottom graph, negative x plus 3, it'll be a closed circle. So just like before when you graphed an inequality, this would be an open circle at 1, shading to the left. This would be a closed circle at 1, shading to the right. But now, instead of just talking about the domain, we're going to now put these onto a piece of graph paper and graph an equation using this same concept. So we have 1/2 x plus 3 for x less than 1 and negative x plus 3 for x greater than or equal to 1. What you will notice in my table is I split that into two colors. I have the blue and I have the red. And I also repeated the number 1. The number 1 is my breaking point. I need to evaluate the number 1 for both the top equation and the bottom equation. So therefore, in my table, I need to use the number 1 twice. So again, I call number 1 the breaking point. So sometimes in my table, or like on your table, I darkened the line between them to give me that idea or reminder that the graphs do not overlap at that value. So x is less than 1 come from this top equation here, 1/2 x plus 3. So I'm going to plug -1, 0, and 1 into the top equation. So this is like 1/2 times -1 plus 3, 1/2 times 0 plus 3, and 1/2 times 1 plus 3. And then you're going to get your values. So 3 minus 1/2 is 2.5. 0 plus 3 is 3. And 1/2 times 1 is 1/2 plus 3 is 3.5. So I can see that my y-intercept is 3. So over here on my graph, I plot the point 0, 3. At the point 1, 3.5, I need to have an open circle. And again, my slope is a positive 1/2. So I could go down 1 and over 2 to get myself a couple other points. And I draw in the line. That line represents all x values less than 1 that make the equation 1/2 x plus 3 true. At 1, that line stops. It gets infinitely close to 1, but does not exist at 1. At 1, my graph is going to jump to the new equation, -x plus 3. So now I'm going to plug 1 into -x plus 3, and I get 2. I plug -2 into x plus 3, and I get 1. Plug in 3, and we get 0. On the second equation, it's equal to the value 1. So this is a closed point on my graph because it's equal at that point. So when I plot the point 1, 2, I'm going to plot a closed circle. Any point except the breaking points are always closed. So all these dots on the blue dot line were closed. The 2, 1 is a real point. 3, 0. 4, -1. 5, -2. Etc. So my red line has a negative slope, so it's going down. And then we want to talk about domain and range. So, does every value of x have an answer for y? Can I plug in every x number and get an output? Yeah, because it's x less than 1 and x greater than or equal to 1. So they overlap, they match up, they meet. So my domain is -infinity to infinity, or all reals. Because every value of x has an output for y. What is my range? The range are the y values. Well, if I look at this graph, My y values, both arrows are going down, so everything in the negative region is covered. But then the highest point on my graph is right here at that open circle. So what it means is we're getting infinitely close to the 3.5, but we never quite get there. So my range is all the y values less than, but not equal to, the highest point on the graph, which is 3.5. Is this a function? Is this a function? Does it pass the vertical line test? Yes, it does. Because here, where the only 2 points could overlap, one is open and one is closed. Therefore, there is only one output for one. So yes, this is a function. Is the function 1-to-1? Does it pass the horizontal line test? No. So it is a function, but it is not 1-to-1. Okay, graph the function g of x equals x plus 2 for x values greater than or equal to 2, and negative x plus 4 for x values less than 2. So 2 is my breaking point. So that means this graph changes or transitions from one function to the other at the value of 2. X is greater than or equal to 2. So that means the top equation, in this case, is my lower numbers. So the top equation is my lower numbers in my table. And then x values less than 2, use the negative x plus 4 equation. So don't just assume the top equation goes into the top part of the table. You have to look at the values and pay attention to where they plug in. When is x less than 2? When x is 1 or 0. X less than 2 has an open circle. So whatever point I get here is an open circle on my graph. So negative 0 plus 4 is 4. Negative 1 plus 4 is 3. And negative 2 plus 4 is 2. So I plot the point 0, 4, 1, 3. And I have an open circle at 2, 2. Again, these are x values less than 2. When is x less than 2? Well, that's to the left of 2. So this line or graph goes this direction. The upper equation is x plus 2. So 2 plus 2 is 4. 3 plus 2 is 5. 4 plus 2 is 6. At 2, 4, it is a closed point because it's x greater than or equal to 2. So I plot the point 2, 4, 3, 5, 4, 6, and that line continues infinitely upward. So again, my domain overlap at 2. So like the bottom part of the equation is saying negative infinity up to 2. The top part is saying including 2 to infinity. So they come together to give a domain of all reals. You could pick any value of x and get an answer. I could ask you to find x equal 10, and you would know to plug it into the top equation. I could ask you for x equals negative 10, and you need to know you plug it into the bottom equation. So again, finding the function value is another way of looking at these points. What is my range? Well, my range comes from the lowest or highest y value. In this case, both graphs are pointing upwards infinitely. So my y values are going to be greater than the lowest point on the graph. And the lowest point on the graph is at 2. So my range is y greater than, again, the point 2, 2 is an open circle, so it doesn't include 2. So my range is y greater than 2. This is once again a function that is not one-to-one. This is a function that is not one-to-one. It passes the vertical line test. For every x, there is only one y. Your piecewise function, like I said before, can have more than 2 equations. So here's an example where we have 3 equations being pieced together. If there are 3 equations, then there are 2 breaking points. So there will always be one less breaking point than the number of equations. 2 equations, 1 breaking point. 3 equations, 2 breaking points. 4 equations, 3 breaking points, and so on. So this table breaks at all of the jumps over here. So we have breaking points at -2 and at +2. So we want to look at our table and we want to determine what x values are less than -2. Which equation go with that example? Well, this inequality right here represents the x values less than or equal to -2. So what that means is that -4, -3, and -2 are getting plugged in to -x plus 1. And that I have a closed point at -2. So a negative and -4 is a positive 4 plus 1, which is 5. A negative and -3 is positive plus 1, so you get 4. A negative and -2 is positive plus 1, so you get 3. So you have -4, 5. -3, 4. -2, 3. And again, this graph continues for all x values less than or equal to -2. So it is going infinitely up and to the left. The middle equation is all values from -2 to 2. So that's this equation here in the middle. It includes -2 and +2. Now, if there is no x, what does that tell you about the slope? If there's no x, Gretel, it's 0. Perfect. So if the slope of the equation is 0 and it's -3, that means from -2 to 2, my y value is unchanging. It is always -3. That is a horizontal line with a slope of 0. And for x values greater than 2, we use the top equation. So 2 minus 1 is 1. 3 minus 1 is 2. 4 minus 1 is 3. And so on and so forth. At 2, 1, it is an open circle because its x value is greater than 2. And this has a positive slope, so once again, my line is increasing infinitely. Is this a function? No. Why is it not a function? Stephen? Exactly. There are 2 closed points at -2, therefore not a function. For every x, there is not a unique y. There are 2 y's for x equals -2. What is my domain? What is my domain? Does every x value have a point in this equation? Yeah. So therefore, my domain is, no trick question, all reals. Your range is not quite so easy. The y values both increase on the red and the blue. So the lowest y point between the 2 of them is at 1. So every y value greater than 1 will have a point. What y value can we not forget that happens down below? What other range values included, Stephen? Exactly. So I have to write y equals -3 also. So the y values are greater than 1 and include -3. So what you're going to do for tonight is those next couple problems. You're going to be answering the questions, is this a function, as well as graphing them.